Okay, so now we're going to talk about angular momentum. Okay, so just to impress upon you, not to cause any confusion, you have to remember what we just talked about in the previous video when we talked about moment of inertia. That is analogous to mass in translational motion. Okay, angular momentum here, we're going to talk about the rotational inertia of an object. That's not the same as moment of inertia. Moment of inertia is analogous to the mass of an object, whereas rotational inertia is the resistance to rotational change in motion. Okay, so you remember, just as an object at rest tends to stay at rest, and an object in motion tends to remain moving in a straight line, an object that is rotating about an axis will tend to remain rotating about that axis unless it's interfered with by some external influence. Now, like inertia for linear motion, rotational inertia depends on the mass of the object too. Okay, just in linear motion, an object with more mass takes more effort to get it moving. It has more inertia. But unlike linear motion, rotational inertia also depends on the distribution of that mass relative to the axis of rotation. So if you have masses that are close to the axis of rotation, you're going to get it to rotate easier. You move them further apart, it's going to be more difficult to rotate that. So the greater the distance between an object's mass concentration and the axis of rotation the greater the rotational inertia. And there are several examples of this, all around us. If you look at a tightrope walker, for example, they'll often carry these large poles, sometimes with masses hanging from the end of them. Most of the mass of the pole is far from the axis of rotation, which would be at the walker's hands, right? The pole then has a considerable rotational inertia. If the tightrope walker starts to topple over, they'll tighten up their grip on that pole and rotate that pole, but the rotational inertia of the pole resists, giving the tightrope walker time to readjust his or her balance. So the longer the pole they're carrying, the better, and better still if they're big massive objects hanging from the ends. You can also experience a rotational inertia right now if you have a pen or pencil in your hand, right? So consider there are three axes along on a pencil, right? The first axis would be like through the center of the pencil, right? So along the direction of the pencil itself. Now you can easily rotate a pen or pencil around that axis. You just roll it in your fingers, and it's very easy to roll, right? So let's say you have another axis, right? Take one right through the middle of that pencil, and you grab it at that axis, and you rotate it back and forth, right? So you rotate it back and forth this way. You can feel that it's different rotational inertia trying to rotate the pencil this way than it was when you were rolling it. And a third axis will put right at, say, the end of the pencil, right at the eraser here, so perpendicular to that pencil. And then you try to rotate it that way, you can really feel a big difference in how that pen or pencil would respond, right? So you can feel its rotational inertia. For baseball players, right, a longer bat is going to have a greater rotational inertia than a short bat. Once it's swinging, it has then a greater tendency to keep swinging, but it's harder to bring it up to that speed. So a short bat with less rotational inertia is easier to swing, which explains why some baseball players will sometimes choke up on a bat, grasping it closer to the middle of the bat, which shortens the bat, and they can swing it faster. Okay. Also, in the animal world, we've got long legs of a giraffe, right? So those long legs of a giraffe are going to have a greater rotational inertia, and so you're going to get an animal with a really long gait as they run, right? Whereas an animal with short little legs, right, they're going to be running really, really fast. Their legs move really fast because there's smaller rotational inertia. So now I have a question for you, and I want you to think about this question. Below here are two cylinders. One is a solid cylinder, the other is a hoop. Both have the same diameter, okay? But when they're rolled down the same incline, which one will reach the bottom first? Or will they reach the bottom at the same time? I want you to think about that, and then we're going to discuss it in class. Okay, so that's rotational inertia. And just like with translational motion, right, the mass of an object is what resists that, is what that inertia is about, how it resists a change in motion. The moment of inertia is analogous to that mass, right? And an object with greater moment of inertia will resist a change in its rotation more than an object with less moment of inertia. But just like with translational motion, once an object gets rotating, it has a momentum, okay? Now, for a single particle, we can think of the law of conservation of momentum as an alternative way of stating Newton's first law. Rather than saying that a particle will continue to move in a straight line at a constant velocity unless it's acted on by a net force, we can also say that the momentum of an isolated particle is conserved. Both express the idea that a particle moving in a straight line tends to keep going unless something acts on it to change its motion. In the same way, a spinning object or rotating object will keep turning unless it's acted upon by some outside torque. The quantity that expresses this idea for circular motion is called angular momentum. So let's go through a description of angular motion and come up with an expression for it. If we take, for example, this girl pushing this merry-go-round here. As she pushes tangentially on the rim of the merry-go-round, she's applying a torque to that merry-go-round. Now, the merry-go-round's angular speed will continue to increase for as long as she applies that torque. If she pushes harder on the merry-go-round, or if she pushes for a longer amount of time, then there will be a greater increase in its angular velocity. So we want to be able to then quantify these observations. So let's start by, let's apply a constant torque to the merry-go-round for some time interval. By how much will the merry-go-round's angular speed increase? Well, we found previously that the angular acceleration is given by the rotational equivalent of Newton's second law, or the torque over the moment of inertia. Now, by definition, the angular acceleration is the rate of change of the angular velocity. So we get the change of angular velocity divided by time. If we set these two equations equal to one another, we get this right here, where we've got our angular velocity and our time and our net torque and our moment of inertia. Now, if we rearrange this, we can get this right here. Now, thinking about linear motion then, and we've put together and shown you some how these quantities are analogous to one another, right? So the torque is analogous to force. Moment of inertia is analogous to mass. Angular velocity is analogous to linear velocity. So in linear motion then, this expression would look like this. That should be fairly familiar to you. Here we've got impulse and momentum. So this statement right here is an analogous statement to the impulse momentum theorem that we've already studied. So that tells us then that I omega is the rotational equivalent to momentum. And this allows us then to reasonably define then the angular momentum to be I omega. So we symbolize angular momentum then with a capital L. Its units are written in kilogram meters squared per second. Okay, so the units of angular momentum are those of moment of inertia times those of angular velocity, kilogram meter squared per second. So just as an object in linear motion can have a large momentum, either by having a large mass or a large speed, A rotating object can have a large angular momentum by having a large moment of inertia or a large angular velocity. So our merry-go-round example here, it will have a larger angular momentum if it's spinning fast than if it's spinning slowly. Also, the merry-go-round has a much larger angular momentum than, say, like a toy top spinning with the same angular velocity. And again, we can see each of these analogies between these quantities in linear motion and rotational motion here in this table. So then, since we've defined angular momentum, we can also then talk about conservation of angular momentum. Any change in angular momentum of an object is proportional to the torque, the net torque, applied to that object. So if the net torque on an object is 0, then the change in angular momentum will be 0 as well. That is, a rotating object will continue to rotate with constant angular velocity unless it's acted upon by some external torque. So this is the law of conservation of angular momentum. The angular momentum of a rotating object subject to no net external torque is a constant. The final angular momentum will be equal to the initial angular momentum, which is the same as saying that for forces, if the net force is 0, then there's not going to be a change in momentum. So remember, moment of inertia takes into consideration how mass is distributed in an object, right? The expression, remember, for moment of inertia was this right here. So it's dependent upon how mass is distributed in an object, okay? So like for our merry-go-round example, right? If you sit in the center of a merry-go-round, you're going to spin faster for the same torque than if you move to the outside of that merry-go-round. When it comes to angular momentum, to figure out the direction of angular momentum, because it is a vector, we can do what's called a right-hand rule for it, where basically if you take whatever the thing is that's rotating and you put your fingers in the direction of rotation, like this is a wheel on an axle, the wheel is spinning this direction here. So if you were to wrap your fingers around that axle in that direction of motion and stick your thumb out, the thumb points into in the direction of that momentum. So if the wheel were spinning the other direction, you'd have to wrap your hand around the other way, and the momentum would point outward. And it's called the right-hand rule because you use your right hand when you do this, right? So because moment of inertia is dependent upon how that mass is distributed around the axis of rotation, if you take, for example, this fellow right here sitting in a spinning chair and he's holding these weights out, we've got a much larger moment of inertia right here, right? Because here's our axis of rotation and he's spinning around it. He's going to have a much larger axis of rotation. He's going to spin slower. When he brings his hands in, he's going to spin much faster. Figure skaters use this all the time when they go and do their twirling thing on the tip of their ice skates, right? You put the arms out like this, you increase that moment of inertia, and you spin slower. When they bring their arms and legs in, they'll spin faster and faster and faster. Okay, so there's two really great examples in your textbook using looking at angular momentum. Make sure you take a look at those, and we'll see you in class.